non-standard, I will define that if it comes up on the test. But the principal argument you must know. If I ask you to solve z to the 10th power equals to 1 plus I, can you do it? Z to the 10th power equals 1 plus I. Can you find me all 10 solutions? At least symbolically, right? Now, if I wanted to be evil, I'd be like, put them in Cartesian form. But I wouldn't do that because I don't want to grade that, right? I would say, put it in polar form, please. And maybe don't use 10, right? I think I can probably understand whether or not you understand that material by testing like, oh, I don't know, the third root. If I test like z cubed equals to, 3 plus 4i or something like that, I can pretty much find out what I need there. Although sometimes I ask the fourth power just because it's easier, because the fourth root of unity is I, Let's see here, what else can I tell you guys? I've spent a fair amount of time talking about the discontinuity of the logarithm at the angle jump. I wouldn't be surprised if I ask something about that. I do want you to understand that. So if you don't understand that, please spend some time thinking about it. Like the proof is really simple. You have a function on the plane. You have a point which is in the domain of the function, right? So is it continuous there? Well, if the multivariate limit exists, then all of the path limits have to exist and they have to agree. This is calculus 3, right? So if you can approach from the top of the path and you can approach from the bottom of the path and you get different angles, that means you have two path limits which don't agree. Therefore, the limit does not exist. Therefore, it's not continuous. For it to be continuous, the limit would have to exist and match the value of the function at the point, which it does not here. As I explained, this path limit gives me natural log plus I alpha, and this one gives me natural log of r plus I alpha plus 2 pi. We can't have both of those, right? Let's see here. Anything else I want to tell you guys? I'll probably ask something about the branch, where the branch goes for like a logarithm. So if you think about it, if I ask you to like graph it and ask like a graphically analytical question, it pretty much has to be a linear one because I've just got done telling you that when it's quadratic or cubic, it's truly horrible. Like what the thing does, it's all kinds of wacky curves. So it pretty much has to be a linear one, in which case it's more or less like this, right? It's more or less like this. Now if I ask for if I ask for like a quadratic or if I take the log and I feed it something more exotic, you probably have to be able to answer the question just on the basis of like where the branch has to, just on the places where the logarithm 0 probably is enough to answer the question. So we saw that in like the last part of the last quiz question. Those questions are not as hard as they seem, right? They have simple answers because of just looking at t equals to 0 for the branch. All right, something else I was going to tell you guys. So here's one that worked out pretty nice though, like this one. The branches were interesting, but they actually were vertical like that. This particular situation is an example of one that is not as stupidly simple as the linear one, and yet not impossible to graph with your technology. So here's the kind of, that's the only example I can think of off the top of my head, and like everything I've shown you, where the branches were interesting and also accessible to our means. What do I expect you to be able to graph in here? Lines, parabolas, hyperbolas, ellipses, circles, pretty much, right? Sine, cosine, cosh, sinh, your usual culprits from calculus. Oh man, problem 51 is a fantastic test question. Look at this. Show that a function which is just real or just imaginary, if a function is holomorphic and pure imaginary on a domain, it's necessarily constant. This is a time-honored test question, right? This one's nice. You're noticing a theme here. The nice test questions, they basically boil down to understand what you're trying to prove and then use the gradient simplified by the Cauchy-Riemann equations, and that's pretty much the solution every time. Oh, I found you guys asked me about this one. Look, the solution has something in here that I didn't tell any of you in person. Here's the thing I didn't know about that I should have told you about if I knew about. I finally found it. This is the simplification. What you want to do is multiply the top and the bottom by e to the minus I theta over 2. Upon having done that, it simplifies like so. And there's the formulas that everyone loves to put in their books. Now, I told your grader to give you full credit if you did not do this. But here's the path to get the magical formulas you guys took pictures of in my books. Excuse me, Dr. Sprano's book, which is still in my office. Let's see here. So you might, look, problem 53, I'm kind of, I have mixed feelings about. On the one hand, hooray, there's the fiber. There's the inverse image of W. It's this set. Now, but if you ask me what's it look like, I don't know. I don't know what it looks like. I know that it's this. What does it look like? I don't know. If you ask me what's the inverse image of like the exponential, I can tell you, right? It's this like bunch of points that are 2 pi separated in the imaginary. So like this example, I have a formula, but I spent a couple pages trying to understand it geometrically, and I never feel like I really got anywhere. So that's what essentially the next one is. But deriving the derivative of an inverse function, the inverse function theorem, it's important for you to know that, right? Because knowing the derivative of the inverse function theorem gives you license to do these steps, which is how you really should derive derivatives of inverse functions, right? The alternative is to find the formula in terms of the logarithm, take a branch, differentiate that. You can do that. It'll get you the same formula, but woof, it's not as easy. I think I do it both ways for one of these. Let's see here. So I hope you understand this calculation. We can do this same song and dance for sine, for cosine, for tangent, for cotangent, for hyperbolic cosine, for sinh. Any of these functions which are built from exponentials or imaginary exponentials, we can play this game. We can convert the defining equation to a quadratic equation, and then we can solve it for the exponential. Well, having solved for the exponential, we take the log. That's the formula for the multiply valued inverse function. Taking a branch of that is the branch cut of the original function. This same method of analysis works for all of our elementary functions, because they're all based on what? They're all based on the exponential, which means that the inverse in one way or another is all based on the logarithm. All right, so it's like the same thing every time. So I have not looked at mission 1 much today. I mean, not at all, right? Does it still matter? I think it does. I don't see myself asking you anything about that really complicated. It's not that complicated, but the formal question at the end of the mission 1 that was on like the construction of the complex plane by, so what I want to say just in conclusion here, guys, is make sure you know your basic stuff, like prove the product of the conjugates, the conjugate of products, product of conjugates, the multiplicativity of the modulus, like the length of a product of 2 complex numbers is the product of their lengths. Those things I do sometimes test on, and you should be ready for those, right? And do them the right way, which I tried to guide you through in the homework. The other thing I would say is I have been trying to give you guys a geometrically interesting problem, and it keeps blowing up in my face. Like I've been trying to give you the equation for an ellipse or hyperbola in terms of moduli, right? But I have inadvertently picked like things to make it just a point, right? Or nothing at all. Don't confuse that with it not mattering. It matters. There are versions of those problems which become interesting because instead of it not having a solution or just being a point, it actually is a full honest to goodness hyperbola or ellipse. And here's one. How about this? Can you tell me what this is? What's this one? If I do z minus I equals to, say, modulus of z plus 1. What's this? And you should be able to embrace the idea of solving some of these problems geometrically. So this is what? The distance from, that's the distance from I, right? This is the distance from z to what? -1, which is over here, right? And what is this saying? This is saying that the distance from this, it says the distance from these 2 points is equal. What is that? Aren't you guys in geometry? Oh, that's right. You guys don't believe in distance in geometry. What kind of geometry is that anyway? Tell Dr. Sprano that we've known about distance for 1,000 years. Why is it in his course yet? Tell him. This is a line. Yeah, it's a line. It's a line which takes those as a perpendicular bisector like that. See, if you take the collection of points which are the same distance from given points, that forms a line. If you take, if I, instead of making this, if I said this plus that was equal to 10, that's an ellipse. If I change that to a minus, it's a hyperbola, unless I got really unlucky again. But I think the unlucky thing is if I put a 2 there. Anyway, I will double check. If I put a problem like this on the test, the point is for you to understand geometrically what the equations mean. And yeah, you can convert to xy's, and that's good. But think about z. Don't just think xy. Yeah? All right, anyway, I'll shut up. But I will make an announcement to clarify what, if any, proofs in the notes I expect you to be responsible for. So unless I send you an announcement, you can assume that you don't have to be like studying the proofs, okay? Definitions you need to know, though. All right?
Thank you.